I want to report, summarize what I've learned about dust back reactions over the years. Um, I think by now, everybody should agree that we have a lot of disks with substructures, but the important thing is that many of them are axisymmetric. And I want to concur with Jeremy yesterday. There are many other possibilities than planets that can drive axisymmetric structure. And I want to throw in one even more possibility, is that dust back reaction itself already can drive axisymmetric structure. So this is the simulation I've done quite a while ago. And I think it was a big mistake I didn't put in this plot. So this is a radial and azimuthal direction, and you are looking down from the top down. And clearly, you see axisymmetric structures happening in the dust component. So I think this is a nice possibilities. And I have learned the properties of all these filaments. The first of it is a radial separation between the filaments. In a laminar disk, it's roughly about 0.2 gas scale height. And in turbulent disk, it can be as wide as a few gas scale height. And this separation does not seem to be sensitive to the particle size. And important thing is that it clearly decreases with the solid loading you have. So the higher the solid abundance, the separation becomes smaller, and you got more filaments. And this is the radial direction. Also, vertical direction. I also clearly see that you can sediment more when you have a higher concentration. So why this happens? This can actually intuitively understand, because Minkai also mentioned this effect. If you have a back reaction from the dust to the gas, you actually increase the inertia of the whole system. So it's hard to move things around when you have dust back reaction. So your effective sound speed is actually decreasing. And this is the formula for the very tightly coupled particles. And this for this approximation to be true, you need to assume terminal velocity approximation. The relative velocity between particle and gas need to be small. So it may not be correct if you are considering modularly coupled particles or even larger. And this effect is actually very strong in transitional debris disk, because in that case, you have a very, very high side to gas ratio. And you do see a lot of asymmetric rings in this case. I think Vlad can talk to you much about this system. Okay, but I don't think my local simulations can convince observers. So I'm moving to global now. And I'm banking on the code Athena++. And these are the reasons. It's a total rewrite from Athena. And it's now 3 to 5 times faster than the old Athena. And the time integrators you have many choices now. It can be up fourth order accurate. And the spherical polar coordinates, you can simulate the full disk, full 4-pi solid angle. And the most important thing for me is they have a static or adaptive mesh refinement and automatic load balancing. So I will not suffer from strong concentration of dust, for example, at a certain mesh block. And I'm responsible for putting in dust particles in Athena++. And it's a very standard Lagrangian superparticles with two-way interactions. And it's now working with mesh refinement. And this is just showing you what kind of typical mesh structures you can have with a global disk. So I already showed the movie. You already see the right-hand side. I also reproduced the nonlinear streaming stability. But the most important thing is that if I test the linear modes, I got a second-order convergence. So it looks like, at least in the local stream sheet Cartesian grid, it is working. And this is the state of art of my module now. I can now simulate curvilinear coordinates with mesh refinements. It's buffering? Yeah, no. So you are looking at the dust density distribution. And because of dynamic time scale is short from inside, you do see the nonlinear behavior and propagating out from inside out. And this is the typical radial drift. And I hope I can convince you this part is very similar to the local simulations. So I hope I'm doing the right thing. So that's about it. So moving on, second topic. How about turbulence? If you have a turbulence, how does it interact with dust dynamics? So I'm basically try to put in a lot of new, MHD simulations to study this effect. But I want to point out, not only drag, there are two effects from the turbulence. One is actually they also have stochastic gravity due to density perturbations. And this effect, I must emphasize, has no mass dependence. It affects all particles of all masses because gravity only gives you acceleration. It does not differentiate. So whatever, in any case, you should consider this as an effect. But it turns out it only works for kilometer size and up. That's the more dominant. And I basically gives you a prescription of the effect of turbulence, how it changed the orbital dynamics, including radial eccentricity, and the most important thing, inclination. I think this is the only study that can provide you with inclination excitation. And I think this important effect, which is neglected in the collisional study of pentatesimal growth, inclination is usually ignored. However, if you consider this small excitation, there may be very unexpected results. And I only saw like 2 studies, including this, and they are conflicting. One has a runaway excitation of inclination if you put in a small inclination. The other doesn't see it. So I think it's still an open question to be answered. But of course, now for everybody interested here, I want to focus on the small particles. So I set up a these 6 models with ideal and non-ideal MHD. And this is alpha stress. And I have ideal MHD, and this is the vertical profile of alpha stress. And you can see I nicely have a dead zone here with a couple of 10 to minus 4 in alpha stress. And then I put in a lot of particles with Stokes number 0.1. And this is the equilibrium scale height of particles as a function of time. So I basically reach a balance between vertical diffusion from the turbulent drag and the cementation. Okay? But the problem is that if I have alpha stress, and I put in this famous formula from 1995, Zubios et al., this is the prediction. Way too low. So it must be wrong. I hope I'm not offending that side. Okay, why is that? If you look at the energy profile, this is the kinetic energy in the gas. Between ideal MHD and dead zone, they are not much different. And why you still have a lot of such kind of kinetic energy in the midplane? It's still disturbed by the surface layer of the turbulence. So you still have a lot of kinetic energy here. And we are actually doing one step further. Oh, so this is what I want to emphasize. Don't use alpha stress to predict your vertical diffusion of particles. So we can do one more step better. We actually measure the diffusion coefficient in the gas in all 3 directions. And this is the result. For the ideal MHD, the red lines, they are almost coincide with each other, and also coincide the alpha stress I showed earlier. So for ideal MHD, it's pretty much isotropic. But in the dead zone, it's very different. This is vertical. This is horizontal. And the alpha stress is here. So the vertical alpha diffusion is more than 1 order of magnitude larger than the alpha stress. So this is clearly an isotropic disturbance. So if I use the vertical diffusion coefficient into this formula, then I recover the scale height of the particles. So when you are consider non-ideal MHD disk models, you really need to take into account this anisotropy of the gas fluctuations. Okay. So the pebbles are still significantly stirred up by the gas. And I need to point out here, 0.02 is where the laminar disks give you, but given by the streaming turbulence. So you are still excited by almost 1 order of magnitude up, very puffed up. So as Ming-Kai said yesterday, this is very difficult for the streaming instability. So let's find out if that's the case. So in the ideal MHD, I turn on back reaction and systematically increase the solid loading. And this is the radial concentration as a function of time. Indeed, I don't see any concentration, except maybe transient here, and then dispersed. So in the ideal MHD, it looks like it's indeed very difficult to get the radial strong concentration and drive planetismal formation. But in the dead zone, I still see strong concentrations above 2%. So it still works. Back reaction still works to concentrate themselves to high density. And you can still also see the solid abundance effect with more filaments forming with higher solid abundance. Even higher density, I saw a very, very strong concentration at 2%. So these are the messages. I think the critical solid abundance does not seem to be sensitive to sedimentation at all. So if you consider this local condition, I think it's maybe not sufficient to predict planetismal formation. I'm not sure about necessary part, but I know it's not sufficient. So I don't have a prescription for you yet, but I believe these two factors, solid abundance and strength of radial diffusion, will determine where planetismals are formed in turbulent disks. Okay, the final topic. What about if you have a planet? What does dust back reaction do? So I basically set up a 2D local sheet with a planet with dust, single sized. And this is the no back reaction results, and we covered decades of study. And now I systematically vary the mass of the planet, the size of the particle, and the solid loading. So I have a 3D data cube, a lot of simulations. But I will only summarize interesting trends for you here, hopefully. So the first effect, how does the dust bag reaction affect the spiral structure? This is a measurement of the spiral structure in the gas. And you do see that the pitch angle decreases with increasing solid loading. So this means that the spiral becomes less open when you have more dust. And the dashed line is the theoretical asymptotic limit of the spiral arms given by the linear theory. And I modify it by this factor because originally it depends on the gas scale height. And according my sound speed argument, you should multiply the asymptotic limit by this factor. And indeed, you also see the trend of increasing solid abundance with decreasing pitch angle. So this looks like nicely recovered the prediction. But this is for small dust. What about large pebbles? I think you can pretty much see there's no change. So this is one thing to demonstrate that this sound speed argument only works for very small one, but not very large one. Second feature, how about the gap? How does it affect gap structures? For low mass planet, this is the no backgradient results. And with increasing side loading, your gap becomes much deeper this way. And this can also be understood by the sound speed argument because the torque is sensitive to the gas scale height, to the second order, second power. So that's why you have a very sensitive dependence on the depth, but not the width. Not the width. So my interpretation is that the solid loading does not change the resonance locations of the spiral excitation. That's probably why you still get the same width. And for very, very high mass planet, this depth effect is solid effect is gone. And the reason is that the dust here is pretty much depleted. So you don't really have a solid loading effect. That's why you don't see anything here. But you do see near the edge, as Flood already reported yesterday, you do get something pushed out in the gas. How about large particles? It's even more dramatic. I don't have any gap anymore. The gas is pushed out from the inside out, and the whole gap is gone. And even with a high mass planet, you still see the edge effect. Everything is gone. What does it look like? It looks like this. I cannot really tell there's any gap around the planet in the gas. And I will talk about the particles part later. And how about the radial drift? This is what I see. Without back reaction, you do collect dust particles in the outer edge, and also some accumulation in the inside because of the planet pushing particles away. However, if you turn on back reaction, everything brokens up into small vortices. And the reason is that the particles start to accelerate the gas when they are where they are accumulating, but inside they are still subcapillary. So as long as this gap becomes sharp enough, you start become unstable, and you generate all the vortices here. And because of all these vortices, this gap also becomes a little bit filled up by the particles. I need to hurry up. And okay, the same thing happens with large pebbles. You also see a lot of vortices happening here. But the interesting thing for the large particle is that you see a fast depletion. There's no dust because of radial drift. But in this case, they're still here. So with back reaction, you can still filter your particles through the planet. So that's quite different results. And how about vortices? With large enough mass, you generate vortices and particle concentration, but with back reactions, they are all gone. No vortices at all, in both the gas and the particles. So these are all I want to say. And I think dust back reaction is still very complex and can change a lot of things. They can drive asymmetric structure, drive planetism formation even in the dead zone, and change for the observers the substructures in this planet interaction. So that's all I want to say. Thank you.
Okay, thank you. We have time for one quick question. Yes?
That talk. There's more than one question, but I'll just ask one thing. So about the scale height of the dust in the presence of turbulence. Just a comment. I believe there's a measurement of the scale height of the dust in HL tau, submillimeter dust. So this is getting quite interesting. It's a two-part question. Sorry. What were your assumptions about the gas? Was it an isothermal?
Yes.
So there was no true stratification in the true sense, which can. This is coupled to the other part of the question. have you done an analysis of the nature of these hydrodynamic fluctuations in the midplane? I mean, are they homograph-like eddies, or is there a, if you Fourier analyze them in space and time, do they follow some dispersion relation, like the inertial wave dispersion relation, or?
I only have answer for ideal MHD, and I think it's pretty comarograph. But I have no answer for that zone yet, for you.
Because if they are waves of some sort, the anisotropy that you measure could be quite different.
I
in the
agree.
Presence of an vertical entropy gradient. Or
I
something.
agree. Yes. Yeah. I agree. Yes. Yes.
I'm sorry, we have to move on because we are already quite late. Thanks again.
Sorry about overtime. Thank you. Thank you. Thank you.
And the next.